Welcome to the lecture on polyphenylene sulfide for thermoplastic resins, PET 371. We are starting a series of the sulfur and oxygen containing thermoplastics. These include polyphenylene sulfide, polysulfones, polyether imide, polyether ether ketone, and polyphenylene oxide. You will see this slide a whole bunch, and part of the reason these are all grouped together is because they either have sulfur or oxygen or both, and a lot of aromatic rings present in the polymer backbone. This makes them very rigid and stiff, and also gives them interesting properties as a result. So the first one we're going to talk about today is polyphenylene sulfide. This is polyphenylene sulfide. This is its repeat unit. This is an engineering thermoplastic. Its TG is 88 to 90 degrees Celsius, and its TM is 285 to 288. This is a really high temperature thermoplastic, very stable at high temperature. It has inherent flame resistance, excellent chemical resistance, and a low coefficient of friction. This was first produced by Chevron Phillips in 1968 under the trade name Ryton, and they still produce this under the trade name now. There are other forms of polyphenylene sulfide. There's an alloy of Teflon and polyphenylene sulfide called Milcon. There's also polyimide polyphenylene sulfide alloy, which is Tribolon, and both of these are produced by Tribal Industries. When it comes to the annual production volume of polyphenylene sulfide, it's about 20 million pounds. So we've gotten away from the billions, we're down into the millions, and that's a pretty clear trend. The more expensive something gets per pound, the less of it is actually sold in the US and worldwide. It ranges from about $1.50 to $3.20 a pound for the 40% glass-filled varieties. So we're getting away from the 15 cents a pound. We're up to at least $1.50. Polyphenylene sulfide is made by solution polymerization. This is done with para-chlorobenzene and sodium sulfide in a polar aprotic solvent, and in the case of this one, the polar aprotic solvent is pyridine. So this is the paraphenylene sulfide. Starting over. Para-chlorobenzene. This is the sodium sulfide, and then it's done in this solvent, which is pyridine. This produces sodium chloride as a byproduct and polyphenylene sulfide polymer. This is available in colors of a natural, so it's kind of an off-white to black. This has a density anywhere from 1.35 to 1.65 grams per cubic centimeter. It has excellent dimensional stability. This produces highly reproducible and uniform dimensions, typical of things found in thermosets. So, this produces a very predictable product. This is mainly due to its particular structure and its high crystallinity. The mold shrinkage is very low. The coefficient of linear expansion is also very low, and it has high temperature stability. Its heat deformation temperature is 260 degrees Celsius, and it can be kept at 260 for short periods of time. But what's interesting about it is that you can keep things at 200 to 240 Celsius for long periods of time. So you would use polyphenylene sulfide in a situation in which you needed that high temperature stability. However, if you get much above 350 Celsius, you start to cross-link the polyphenylene sulfide, which, if you want it for thermoplastic purposes, is not advantageous. This is a very high-strength polymer. Its tensile and flexural moduli do increase with increasing temperature. They tend to level off at 130 Celsius, but they can maintain this decreased level up to 260 Celsius. So it can keep high temperature properties for a long period of time up to 260 Celsius. Its tensile strength can be up to 2,000 psi, and its flexural strength can be up to 34,000 psi. It has very high impact strength as well. So again, it's an engineering thermoplastic. It has excellent mechanical properties and at high temperature. Polyphenylene sulfide has inherent flame resistance. It does not require flame retardants. You can make it burn, but you have to force it. And it burns at a very suppressed rate. And when it comes to halogenated plastics, it produces very, very little smoke. It actually can have a limiting oxygen index higher than PVC. So when we can compare polyphenylene sulfide or Ryton, to, say, polycarbonate or nylon 6,6, it's very, very high. Again, this minimum should actually be 22. Polyphenylene sulfide also has high chemical resistance. It is virtually insoluble below 200 Celsius. Above 200 Celsius, it's really only susceptible to aromatic and chlorinated solvents. It has very high environmental stress cracking resistance. It's better than polysulfone and polycarbonate, which are amorphous and have better toughness. Polyphenylene sulfide coatings are highly corrosion and abrasion resistant, and they're often used in the corrosion protection of metals. In atmospheric temperature, it has a degradation temperature of 815 Celsius, and the products of decomposition are hydrogen gas, methane, carbon monoxide, carbon dioxide, and carbon monoxide disulfide. So it's not as innocuous as some other things, but you really, really have to blast this with heat in order to get it to decompose. It has a very, very high flow rate, so that can be a problem in processing. It has the ability to wet different fillers, which make it really good for filling with glass fiber. It's also sometimes filled with iron oxide. And when you fill polyphenylene sulfide, you get a synergistic effect. In other words, the product of glass fiber and polyphenylene sulfide is better than just the sum of their two parts. When you fill it with up to 40% glass fiber, you get a 300% increase in impact strength. And because polyphenylene sulfide wets glass fibers so well, you can get up to 70% loading of fillers. So in other words, you're really just adding polyphenylene sulfide to glass fiber. But the thing is, because it's so expensive, putting in much less expensive glass fiber can really reduce the cost of using the polyphenylene sulfide for your application, which of course is always a concern. Not that you would have a lot of polyphenylene sulfide laying around, but if you did have any pre-consumer parts like sprues or runners, it is 100% recyclable. And this is not always found. Oftentimes when you have regrind, the regrind reduces the properties of whatever it's added to. But in the case of polyphenylene sulfide, that is not the case. Regrinds don't cause any appreciable changes in properties or processability. So you retain all of your properties and you can reuse that really expensive polyphenylene sulfide. It has good moisture absorptivity. It's fairly low over a 24-hour period, and has very good electrical insulating resistance. Now, why would you use polyphenylene sulfide? It has about the same electrical properties as, say, polyethylene, which is much, much less expensive. If you needed something that would insulate well, but also could withstand very high temperature, that's where you would use polyphenylene sulfide. If it's just withstanding normal temperatures, say, in a household setting, you would not be using polyphenylene sulfide. You can process polyphenylene sulfide by injection molding, compression molding, rotational molding, and this is often how coatings are done. Coatings are sometimes done in a slurry, or a fluidized bed, or electrostatic spraying. When it comes to fluidized bed or electrostatic spraying, what you're actually doing, in a slurry you would actually have some sort of solvent, but in fluidized bed or electrostatic spraying, you're actually using powdered polyphenylene sulfide. Electrostatic spraying is usually for a metal coating, and that's what the application of polyphenylene sulfide is most often for. You cause a charge to be across the surface of the metal, and the particles of polyphenylene sulfide are attracted to the metal part, and then you put it through an oven, and then it melts the polyphenylene sulfide and coats it on the surface. So that's what this is often used for powder coating. Its process temperature in the melt is up to 345 degrees Celsius, which is high, and you have to keep your mold up to 149 degrees Celsius. The largest applications of polyphenylene sulfide are electrical and electronic components, interconnection devices, coil forms, terminal boards. It is often used also for protective coatings, so oil-filled pipes, valves, fittings, couplings, and gear pumping components, vanes, impellers, housings, and diffusers. So things that have to withstand a lot of impact. And again, you would use this for electrical or electronic components in areas where you really need the high temperature resistance. This is also used for under-the-hood components for automobiles, flow control valves for heating systems, fuel line connectors, fuel tanks, carburetor parts, ignition plates, exhaust gas return valves to control pollution. So these are all parts that would have to withstand either chemical resistance or heat resistance or both. And so that's where polyphenylene sulfide comes in handy in place of traditional metals. This is often used as housings for hair dryers or small cooking appliances or microwave components. It's also used as a release coating in its coating form for molds, cookware, or industrial containers. Also, because polyphenylene sulfide can be sterilized, it is also used in medical and dental applications for things that are not just single use, but reused items that must be sterilized after a patient, or after they're used on a patient. So here's an example of why you would choose Riton, polyphenylene sulfide, versus a metal. So this is a Riton fuel line connector, and this is a metal fuel line connector. And this is the Riton one after use, and this is the metal one after use. Let me see here. This is a simulated environmental simulation. These weren't actually in place for 10 years, but this is what it would look like after simulated 10 years. And so this is what the metal looks like after 10 years. This is what the Riton looks like after 10 years. So in other words, it's just a little grungy, whereas this is significantly corroded. So that's why you would choose Riton versus, say, your traditional metal connector. So this concludes the polyphenylene sulfide. We are going to move on here to polysulfones.